In this video, I will walk through a proof of Theorem 3.7, which says that every connected graph containing cut vertices has at least two end blocks. So back up to our example for a second. Here we had a graph containing at least two cut vertices, and it had 5 blocks. 3 of them happened to be end blocks, but certainly there were at least two end blocks with this. Now, as another example here, what if I just had the path P4? Let's separate this into its blocks. So this vertex and this vertex are cut vertices. And when I look at the blocks of this, let's call this A, B, C, and D. What would my blocks be here? Well, my blocks would be A and B together. If I included C, B would be B would be able to separate that. So this is a block, B1. This contains just one cut vertex. We also have the block CD. This time C is the cut vertex. We have these 2 blocks. And we have the block, so be careful here, we have the block BC. Right, this is also a block because it's non-separable, and it's maximal. The addition of any other vertex in this would be separable. So these are my blocks of the path, and notice that B1 and B2 are end blocks. Sorry, just say end block. This is sort of the extreme, is where we just have 2 end blocks. This should remind you of the theorem we saw earlier, where every graph with cut vertices has at least two vertices that are not cut vertices. It was the same for the paths. These were on that extreme where they just had 2 vertices that were not cut vertices. And this is our proof will follow a similar flavor to the proof of that theorem, but we'll have to adapt it a little bit. Every connected graph containing cut vertices has at least 2 end blocks. So let's prove this. Proof. All right, before I do that, let's talk strategy for a second. I'll go back up to this one. Notice I have this end block here and this end block here. These are the ones that are going to sort of come out in the proof. The idea is I'm going to take, remember when we showed that there were two vertices that were not cut vertices, we took a longest path in the graph, and the end vertices of that path were the vertices that weren't cut vertices. I'd like to do something similar, only I'm not going to look at a longest path. Rather, I'm going to look at the collection of all the cut vertices, and I'm going to find a pair of cut vertices whose distance is maximum. So in this graph, it would be U and Y. Their distance is maximum over all pairs of cut vertices. So this is sort of the analogy of finding a longest path. So we take these 2 cut vertices, and the idea is this U is going to contain cut vertices, is going to be a part of a block that doesn't involve the path from U to Y. Similarly, Y is going to be a part of a block that doesn't contain the path from Y to U. Those are going to be the end blocks. So let's see how this works. So first off, if G contains only one cut vertex, then every block is an end block. And we're done. Right? Block, remember, is an end block, remember, is a block with only one cut vertex in it. So if G only has one cut vertex, every block's an end block. So G contains at least 2 end blocks, or at least 2 cut vertices. Of all pairs of cut vertices, select U and V such that of all pairs UV of cut vertices, select U and V such that distance from U to V is the maximum. All right. So let's find a path between U and V. Let P be a UV geodesic. Say P is equal to U, equal U0, U1, U2, we have some number of vertices, UK minus 1, UK, which is V. And we know K is at least 1. So it is possible that U1 is equal to V and my path is just length 1. That's possible. That's okay, right? That would be the case in the path we looked at earlier. I find my pair of cut vertices whose distance is maximum. Well, that's B and C, and I find a path between them. So B and C might be the only vertices on the path, but that's okay because I'll still be able to find these end blocks. So let's see. Since U is a cut vertex, actually, let me back up a second. Yeah, I mean, since U is a cut vertex, U1 belongs to a block B, and UK minus 1 belongs to a block, let's call it B prime. Right, they have to belong to some block. And it's possible that those belong to the same blocks, right? It's possible V is actually equal to U1. So it's possible that B is equal to B prime. That's okay, because since U is a cut vertex, U belongs to another block, right? U would also belong to B, or B prime. U would also belong to B, but since it's a cut vertex, it has to belong to another block. It's to another block that is not B. Say U is in the vertex set of, we'll call it B naught. To another block, let's say B naught. They use in B naught. Similarly, V belongs to a block a block, let's call it B naught prime, other than B prime. Right, so this is, let me draw a little picture. Yeah, let me draw a little picture just to show us what's going on here. So here's my U, here's U1, U2, here's UK minus 1, and here's V. So right, it's possible all of these guys form a block by themselves, all of these guys all form a block by themselves. It's possible this is all one big block. But U and V are cut vertices, and so they have to be a part of some other block. So here's right, it's possible. It's also possible these could be split up into a couple different blocks. Maybe it breaks down like this. So this would be my B and my B prime. Possibly it's all one big block. But then I definitely have this B naught that contains U, and this B naught prime which contains V. And I claim B naught and B naught prime are n blocks. I claim B naught is an n block. I'll just show this for B naught, and similar argument will work for B naught prime. So if not, then B naught contains a cut vertex, say X. So if this is not the case, then I can find some other cut vertex in here. Maybe it's not adjacent to U. Maybe I walk a little bit and it's over here. Say X. But this is going to contradict my choice of U and V to be cut vertices that are of maximum distance from each other, right? These two are my cut vertices of maximum distance from each other. And if this is also a cut vertex, well, then the distance from X to V has to be greater than the distance from U to V. Now, how can I be sure of that? What if my X here came over here and it ended up being shorter? What if it's adjacent to a couple vertices and then this is adjacent to V, something like that? So we need to argue why that can't happen. But of course, this is our definition of block, right? That can't happen because if X is a vertex in this block and I have U1 over here, then every X U1 path has to go through U. Rather, maybe I should choose V. Every XV path has to go through U, and so therefore the distance from X to V is strictly greater than the distance from from U to V. So I'll say since X and V are in different blocks, and U is a cut vertex, then every XV path contains U. Hence, the distance from X to V, oops, that's X to X, that would be 0. From X to V, I can use my triangle inequality here to say the distance from X to V is at least as big as the distance from X to U plus the distance from U to V. But this distance from X to U is at least 1, and so this is strictly greater than the distance from U to V. And that's a contradiction. So every graph contains at least 2 n blocks. To identify those n blocks, find 2 vertices that are cut vertices of maximum distance from each other. Necessarily the blocks that contain them and no other element of the path are the n blocks. All right, that's it for this section. I'm leaving the rest of the theorems here to the reader. I'll let you read through those theorems, and I'll make a video for the next section. We'll talk about trees.